Hello students, let us now begin Module 4, excuse me. Module 4 is a continuation of Module 3. We are still in Chapter 2 of our textbook, Matrices and Linear Equations. In Module 3, we talked about matrices, saw some examples, and then established matrix algebra, addition, scalar multiplication, transpose, matrix multiplication, inversion, and things like those. We proved a bunch of algebraic rules. But here in Module 4, our focus of attention is systems of linear equations. More precisely speaking, the relationship between matrices and systems of linear equations. Let's begin. We can classify systems of linear equations as homogeneous and non-homogeneous. These are homogeneous and these are called non-homogeneous. What's the difference? Right-hand side is all zero, then homogeneous. Not all of them zero, at least one non-zero, then non-homogeneous. And this expression down here and that expression up there are the same. If you take the matrix multiplication, that is this row vector, scalar product, this column vector, put them together, and that's precisely the same as the left-hand side of this equation. Right-hand side is 0, so we have the first equation as the first row. Repeat it for the next row, all the way up to mth row, and you get this expression. So this matrix equation and this system of linear equation are the same. Same goes for this one and that one. The only difference is C1, C2, C3 all the way to Cm, and not all of them equal to 0. Those are non-homogeneous. Here are some elementary examples. Here's an example of a homogeneous system. It's easy. We have 0, 0 at the right-hand side. Another homogeneous example. Right-hand side is all 0. This time non-homogeneous. Not all of them 0. We have 0, yes, but there are non-zero elements there. Okay, alright. We are particularly interested in homogeneous system in this case. And for homogeneous system, we always have one solution called a trivial solution. Well, let's take a look at either this way of writing or that way of writing. Either way is a homogeneous system. If all the axes are 0, what do we have? Matrix A times 0 is equal to 0. That's always true. No matter what kind of coefficient I have, this is always true. Same goes here. If x1, x2, all the way up to xn are all 0, then no matter what kind of coefficient a11, a12, and so on have, we have to have all 0. So that's a trivial solution. Always a solution. Now, the question is there any more? Is there any non-trivial solution? The answer to that question is going to be answered right here, the main theorem of this chapter. And it'll turn out that if you have more unknowns than an equation, for example, just 3 equations, 5 unknowns, and then 15 equations and 17 unknowns, and so on and so forth. In that case, there will be non-trivial solutions. Before proving those, let's do some example. Let's find out some non-trivial solutions. Let's look at this system. How do you solve it? Well, let's take a look at this expression, and looks like if I add these two equations, this minus c and plus c will cancel out. What do I get? 2x plus 3. So 3x plus 4y is equal to 0, because if I add those up, negative c, positive c will cancel each other out. And looks like I'm going to get y is equal to negative 3/4 of x. Okay, one down, one more to go. Let's put these into either this equation or that equation. The latter equation is a little bit easier, so let's work it out. X plus y, but y is negative 3/4 of x. So that's the second equation. And then let's simplify this. 1 minus 3/4, so this is 1/4 of x plus z is equal to 0, therefore z is equal to negative 1/4. Okay, we're almost there, and let's express all these in a vector form. X, y, z is equals to x, which is arbitrary, and in place of y is negative 3/4 of x, and then in place of z is negative 1/4 of x. Or equivalently, you can write like this. X is common, take it out, 1 comma negative 3/4 comma negative 1/4. You can write the solution set like this. Okay, I'm not gonna write down the set builder notation and everything. I'll leave the details to you. But let's look at the last expression here. And this is the reason why this kind of system is called homogeneous. Because you have some x, which is a scalar, arbitrary real number, times a certain vector. So if I double x, then the solution will be doubled. If I triple x, solution will be tripled, and so on for all direction. That's why this thing is called homogeneous. By the way, if you don't like to work with all those fractions, then it is possible to express it kind of like this, because this is scalar multiplication. You're looking at vectors, all the vectors parallel to this vector. So you can take a bit of a change of variable and re-express like this. So what's the relationship between x and t? Let's see. Let's see. T is x is 4t, right? Yeah. Okay. Okay, that's a change of variable. So these two vectors are parallel. So yes, you can take a bit of a change of variable and then express it the same fashion. Geometrically, you can draw a certain vector and then draw a line alongside it. Oh, never mind. I'll leave all those details to students. Okay, all right. If you open up this cell, by the way, then you have solution, full solution there. How about a little bit harder example like this one? Okay, how many unknowns? X, Y, Z, W, there are 4. And then how many equations do we have? There are 3. So 4 minus 3, so looks like there's going to be 1 degree of freedom, which means I'm going to have one arbitrary variable, whether it was X as before or some other, it doesn't matter. One of them will be arbitrary. The others will be determined by that X. If we have 5 equations and 3 unknowns, then we will have 5 minus 3 equals to 2, 2 degrees of freedom. 2 characters will be arbitrary, but in this particular case, we'll have just 1 character arbitrary. How do I find that? Well, let's see. Let's take a look at these equations, and I'm interested in the third equation because that's the simplest. You see, the others have all x, y, z, and w, but the last equation have no w, so we're going to begin with removing w. So from the first equation and second equation, we can remove w. How can I do that? I'll do this. So equation 1 plus twice equation 2, so it's 2w and minus 2w, they'll cancel each other out. So let's do that. 3x plus 2x, so I'm going to get 5x, and minus 2x, double this, plus 2y, oh, they'll cancel each other too. Okay, alright. Next, plus c minus c, so minus c, and then w will be gone. Plus 2w minus 2w. So this is what I'm getting. 5x minus z is equal to 0, therefore z is equal to 5x. Oh, this is turning out to be a nice computation. We already got one character, one variable determined, alright? Okay, alright. Let's work out and find out the other characters. Somehow we'll have to get the third equation involved, so let's go to the third equation. Let's recall we obtained this equation by adding a first and second. So if you just go back and do everything about first and second and not getting third equation involved, you're not going to get anything. So let's immediately go to the third equation. So if I plug those in, then what we have? 2x plus 2y plus 3 times 5z, 5x, excuse me, is equal to 0 because you see z is 5x. So this one is replaced by 5x. 3 times 5x, that's equivalent to what? 2x plus 2y plus 15x is equal to 0. 17x plus 2y is equal to 0. Okay, I have it. Y is equal to negative 17 over 2. I'm a little bit concerned with these complicated numbers. Let's see. Oh yeah, I'm doing it right. Okay, negative 17 over 2 is something I'm supposed to get. Okay, no mistake so far. Okay, alright. We determined z, we determined y. Let's determine w. We used up this one. We'll have to go back to either these two. Looks like the second equation is simpler. So, alright, what do we get? X plus y, but y is equivalent to this. Oh no, let me rewrite everything. X plus y minus z minus w is equal to 0. X plus and negative 17 to x, okay, that's y, minus z, z is 5x, so 5x, and then minus w is equal to 0, and then we'll have to simplify that. 1 plus negative 17 halves minus 5, it'll turn out negative 25 over 2, so negative 25 over 2x, x minus w is equal to 0, w is equal to, therefore, 25 over 2x. Did I do this right? Obviously, there is a sign mistake, excuse me. So what sign mistake? Okay, yeah, that's right. This is negative y, so yes. We have to have negative 25 over 2. Okay, that was a simple mistake, easily mended. Therefore, we have the solution x, y, z, and w is equal to x, and then what is y? Negative 17 over 2x. And what's z? That's 5x. And then what is w? Negative 25 over 2x. And this can be rewritten as x times 1 comma negative 17 over 2. 5 comma negative 25 over 2. Or if you don't like the denominators very much, then you can just multiply 2 to everything. 2, negative 17, 10, negative 25. Okay, this expression means all the vectors parallel to this vector. 1 comma negative 17 half, 5 comma negative 25 halves. And this expression tells me all the vectors parallel to this one, 2, negative 17, 10, negative 25. But we are talking about the same vectors because we obtained the second vector simply by multiplying 2 to each term, each component. So it's scalar multiplication, same direction. So geometrically these two mean the same thing. And also in terms of change of variable, just x is 2t, so yeah, it holds. Detail is here in the solution. Everything is already there, so you can read about it at the time of your own leisure. At this moment, there's no reason to stay on all these, so let's just move on. Okay, we just had 2 brief exercises on solving systems of linear equations with more unknowns than number of equations. It feels almost like we're back in intermediate algebra. Okay, alright. Let's go to example, it should be example 3. And we have this system, and then if you solve this, then you're going to get x equal to just 0, 0, 0. And of course I got tired of it. You'll have to use appropriate elimination or substitution or both. And if you do it right, you're going to get 0, 0, 0. Okay, alright, let me just move it on. In this case, only trivial solution, nothing else. In this case, we had non-trivial solution. In that case, we had non-trivial solution. One thing to remember, 2 equations and 3 unknowns. 3 equations and 4 unknowns. But this one, 3 equations and 3 unknowns. So here, there's good chance we have unique solution. And trivial solution is always a solution. So you have unique solution as 0. Of course, not always I'm going to get unique solution if you have same number of equations than number of characters, because if we end up repeating the same equation several times, in that case they can be reduced out, or one equation or more equations can be re-expressed using the others, then we didn't really gain any more information, so you're going to lose all those. And those kind of things are related to so-called linear combinations, but we are going to come back and discuss those later. At this moment, let's focus upon this. The fundamental theorem here. This is really fundamental. Consider a system of m linear equations with n unknowns. Whether it can be written as this traditional form or in matrix notation, it doesn't matter. Question, if n is greater than m, which means there are more unknowns than equations, then the system has to have a non-trivial solution. We already have a trivial solution. If you put all zeros, then of course a times 0 is 0. So alright, we have at least one solution there. Are there any more solutions? In this case, n is greater than m, then the answer is yes. There are more. As a matter of fact, if there is one more, then consequently infinity more. And by this homogeneity, if you just simply multiply by scalar multiplication, then yes, we already saw that. But the proof of this theorem is something we'll have to do it in a separate video. It's going to be very significant, but it's not an optional video, because this is so fundamental that I want everybody to go through with it. Fair warning, it's going to be a difficult theorem to prove, but we'll do it.